Today's the day we begin our discussion of the derivative, and you'll spend most of this, pretty much the whole rest of this semester studying the derivative. The derivative is a special type of rate of change. And to understand the derivative, it's good to kind of be able to visualize the slope of a secant line. Now, a tangent line is a line that touches a function in one spot, right? But a secant line is a line that touches a function in two different spots. So we're going to take a look at a function that I'm going to draw up here. I'm going to look at a secant line running through it. Maybe. Okay. So basically, if I take the line that goes through these 2 points, and I call one of those points C, comma, f of x. Well, I guess not f of x. I guess we should say f of c, because that's the way this book defined it. So this is the point C, comma, f of c. And we will let this point right here be c plus, we'll just say delta x, some little change in x. Then the y value that corresponds to that will be f of c plus delta x. So for example, maybe this is the point 2 comma something, okay? Then this is the point maybe 2.01 comma something. So they're fairly close together, the x values are, and we're calling those c. If we imagine finding the slope between them, we will take the second y value minus the first y value, which in this case is f of c plus delta x minus f of c, all over the second x value minus the first x value, which in this case is c plus delta x minus c. Well, c plus delta x minus c is just plain old delta x, right? Okay, so does this look kind of familiar to you?
Yeah, it looks like the instantaneous quotient.
Looks like the difference quotient, right? Just, but with c's and delta x's instead of x's and h's. Make sense? Now if you imagine pulling those 2 points even closer and closer and closer together until basically they're practically the same point. There's so little difference in their x values and their y values that they're practically the same point. That's sort of like taking the limit as delta x approaches 0, right? Okay. That will take it from the slope of a secant line and turn it into the slope of a tangent line. Once we take the delta x or the change in x and we take the limit as that approaches 0 of the function we just discussed, that becomes the slope of the tangent line. It also, in general, if we just have x's rather than c's, it actually becomes what we call the derivative of a function. So the derivative of a function f at x is given by the equation f prime of x. This is set f prime. This little mark here indicates the derivative. F prime of x always equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. You should recognize this as the difference quotient. Now other books use h's, which I prefer in the place of delta x, and I think most of us prefer that because it's easier to write h every time than delta x. So, but you need to memorize one of these formulas. The one I'm going to use is this one. It says the derivative of a function f with respect to x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that limit exists. For all x for which this limit exists, the derivative will be a function of x. That means you will have variables in your answer unless you are finding the slope of a line or if you are finding the derivative at a specified point, and we will talk more about that later. So now's a good time to wrap your brain around this. Slope of the graph, if I say find the slope of the graph, the slope of the tangent line, or I say find the derivative, they're really all the same process. Those three, even if I say the instantaneous rate of change, When we're talking about things very generically, we typically say derivative, and they oftentimes still have x values left in them. When we're talking more specific about an application or at a specific point, we usually use other terminology. The slope at the point, the slope of the graph, the slope of the tangent line. But they all are arrived at the same way, and it requires you to know one of these two formulas. And I'm going to use the one with h's instead. For our first example, we'd like to find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. Now before we launch into this and make a big deal out of it, what kind of graph is it? F of x equals 2x minus 3. What's its shape?
It's a straight line.
It's a line. All lines are straight. But it is indeed a line. And the thing about lines is that they have the same slope everywhere you go. It doesn't matter which 2 points you pick or which 1 point you pick for calculus. They're going to have the same slope everywhere. So before we even work this problem, we know the answer. What is it? 2. We know the slope is 2. Okay? But we're going to work this from a calculus standpoint, so we're going to find the derivative. The derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So we'll make our substitution. If I substitute parentheses x plus h, I get 2 parentheses x plus h minus 3. So that's f of x plus h minus the original function, also in parentheses, all over h. And if I distribute and clean all of that up, I should be able to substitute 0 in for h. Why can't I substitute 0 in right now? I would get 0. Actually, I would get 0 on top and bottom if we really looked at it. But you're right. I would get 0 on bottom. So when we have a 0 over 0, we're hoping that we can remove that discontinuity there, and then we can find the limit. H approaches 0. 2x plus 2h minus 3 minus 2x plus 3 all over h. So the 2x cancels. The negative 3 and the positive 3 cancel to 0. And I am left with the limit as h approaches 0 of 2h over h. And what can I do to those h's?
Take out an h.
I can take them out. So they actually reduce down to the limit as h approaches 0 of positive 2. And what is the limit of any constant? That constant. So it equals 2. So we just showed you the calculus behind the algebra that you have known since about 8th grade. For our second example, we want to find the slopes of the tangent lines to the graphs of the parabola f of x equals x squared plus 1 at the 2 points 0, 1 and negative 1, 2. So we want to look at something that is nonlinear. In order to find the derivative, slope of the tangent line, or the slope of a graph, or the rate of change at a specified point, any of those things, I need to find the derivative, which is just the limit as h approaches 0 of the difference quotient. So let's start there. We know that f prime of x is equal to f of x plus h, right? Well, the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's make our substitutions. We will take x out and we will substitute x plus h. So we have x plus h, quantity squared plus 1. Then we will subtract the original function, which is x squared plus 1. And we will divide all of that by h, and we will attempt to take the limit as h approaches 0. With any difference quotient, if you try direct substitution at this point, you will always get a 0 over 0. So it is your job to algebraically clean it up and cancel out what is causing that discontinuity. What is causing it is the h. So we need to cancel an h on top and an h on bottom. So let's see if we can do that. If we distribute the top out, we get x squared plus 2xh plus h squared plus 1 minus x squared minus 1. And then on bottom, we still have our h. Anything without an h should cancel to 0 if you have done things correctly. So these go to 0 and these go to 0. And I'm left with the limit as h approaches 0 of 2xh plus h squared all over h. Now we can factor an h out and simplify this function. And that tells us that our derivative equals, the limit as h approaches 0 of 2x plus h. At that point, what can I do? Plug in what?
0.
0 for h, and that will tell me my derivative. My derivative in this case is equal to what? 2x. So there's our derivative. That is the general derivative. We are not asked to stop there. Sometimes you are. You're just asked to find the derivative of the function. At this point, we are asked to continue and use that derivative to find the slope at the points 0, 1, and negative 1, 2. And all you do to find the slope is you substitute into the derivative. So we want to find f prime of 0, and we want to find f prime of negative 1. Unless you're writing the equation of the tangent line, you don't need the y values to go with it. You only need the x values right here. So, if I substitute 0 into my derivative, what do I get? 0. So the slope of the parabola at the point 0, 1 is apparently 0. And then to find the slope at negative 1, I take my derivative and I just substitute negative 1 for the x, and that will tell me the slope at that point. What I'd like to show you now is, let's look at this actual graph. If we take y equals x squared plus 1 and we graph it, it will be an upward parabola with a vertex at 0, 1, correct? So we're looking at these 2 points, 0, 1, and negative 1, positive 2. So let's take a look just at 0, 1 for now. If I draw a tangent line to that, what's the slope of the line that I have just drawn there? 0. That's why we got a slope of 0 when we calculated that algebraically. Take a look at the point negative 1, 2. Now it's hard to estimate the exact numerical value of that, but we definitely know that the slope of that line is positive or negative? Negative. So you should be able to at least somewhat verify your answer by looking at the graph and imagining the tangent line there.